In this lecture, we will cover something that's more advanced, automatic differentiation through implicit solvers or operators. And yeah, if you look at the AD we have looked at so far, we can see that those AD are for explicit operators. That is, the functions that has analytical derivatives or composition of these functions. However, not all the operators are of this form. For example, the function may be implicitly defined. For example, here, if you have x1 and x2 and x3, to compute the y, you cannot have an analytical expression for that, such as a sine or cosine or something like that. But you have to solve for y using some iterative solvers. And this can be the difficulty for the typical AD frameworks if you have a function like that. And you can classify the different operators into 4 categories according to whether they are linear or nonlinear, explicit or implicit. So you have a linear explicit operator where the output is just a times x, or just or you also can add up a constant here. And the second category is nonlinear implicit. For example, the sine or cosine or sigmoid or tanh or any other operators that is written in the explicit form. And you also have a linear implicit where you want to solve, and you have to calculate. Well, this is a typo here. You should calculate ay equal x. You have to solve for y given x. And finally, you have nonlinear implicit operators. Well, this expression is given by a capital F x y. You cannot express y in terms of x using an analytical form, but instead you have to apply some solvers to get y. This is an example where you define the function implicitly. And here you define a function f which maps x to y. And from x to y, to compute y, you have to solve function like this. Of course, you can use the cubic formula for finding the roots, but here I assume that we do not have this formula. We want to solve that using an iterative algorithm, such as Newton's method or bisection method, and they works and they work for the computation. So the question is that how do we compute the gradients of y with respect to x? And this is something related to the implicit function theorem. And for our function, looks like this. If you remember the calculus, and so you can just think of y as a function of x and take the derivatives on both sides of this equation. So you get this expression here. So you find that you already have a y prime, and you just manipulate the expression a little bit, you can get this y prime equal 3x prime minus 1 over 3y squared. And this gradient is exact. So that is how you compute the gradients of an implicit function theorem. So in physical modeling, implicit functions, implicit operators is everywhere. For example, let's return to our bar problem. And what if the material property depends on the temperature itself? The coefficient, diffusive coefficient depends on U, for example, here. And if you want to do numerical simulation using implicit scheme, you would have this kind of a scheme here. You can see that UK plus 1 is here. If k is nonlinear, this will be a highly nonlinear equation. You have to solve this kind of equation using, for example, the Newton-Raphson or bisection method. And if you have this kind of a scheme, the question is, how can you perform the same automatic differentiation for finding the gradients of the objective function with respect to the unknown parameters? And this will be covered in the next few lectures. That is called physics constrained learning, a very powerful approach for doing this kind of a problem.